Hello everybody, welcome back to my channel. Hope you're having a wonderful day so far. This is the watch-along of Harvard CS50x 2025 Week 3 on algorithms. I watch these lectures live and upload condensed versions to the channel as you see here. If you would like to join me live, please join my channel as I stream live on YouTube every single day. Thank you guys. Enjoy.
All right, this is CS50, and this is already week 3, our fourth. And this week's focus is going to be pretty much entirely on algorithms, which is exactly where we started the course, recall, back in week 0. But in one of those algorithms, recall, involved a certain phone book, first physically and then virtually. And indeed, in a phone book, of course, you have all of these names and all of these numbers, presumably alphabetized by first name or last name. And we looked for someone back then, namely John Harvard, some of you might have called or texted even perhaps that number at the time. But recall that among the goals of having that whole conversation about finding John Harvard or anyone in a phone book, digital or otherwise, was to talk about just how good the algorithm was. It sort of went without saying in week 0 that the algorithm has to be correct. Otherwise, what's the point of writing it or implementing it in the first place? But we also talked about design. And can you make a better algorithm by thinking a little harder about it, maybe harnessing some of your intuition, and actually speeding things up, as we discussed. So the first algorithm, recall in week 0, 1 page at a time, was perfectly correct, but super slow. And we described its slope with this straight line here. And if that phone book had, say, n pages, where n just means number, it was a one-to-one relationship, because if you add more pages, you need more steps. The second algorithm, recall, where I went 2 pages at a time, was twice as fast, so surely better. Potentially incorrect, though, if John Harvard got sandwiched between 2 pages, but we proposed to solve that by just doubling back 1 page if need be. If you pass the J section, maybe hit the K section, and therefore need to go back at least 1 page. And that algorithm was fundamentally better. Its line was fundamentally lower than the first algorithm's one, because of course it takes half as much time to implement that second algorithm, plus like 1 extra step, just to double back. But the third and final algorithm in our very first week together, recall, was that so-called divide and conquer. And today we'll give it a name again, binary search, by implying 2, because we were dividing in half, in half, in half, again and again. And we got this fundamentally different shape, whereby even if we double the size of the phone book next year, I proposed maybe Cambridge and Alston here in Massachusetts merging together. So you go from like 1,000 pages to 2,000 pages. One of you observed that that's not a big deal, because you need just 1 more tear of the phone book to actually take a big bite out of that problem and go from 2,000 to 1,000, then to 500, then to 250, and so forth pages in the phone book. So this week is really going to be about implementing algorithms, not only correctly, but also efficiently, and really focusing on design. There won't be much new syntax in C. We'll give you a couple of building blocks that solve concrete problems. But this week is really about taking a breather after the past 2 weeks of fairly new, fairly intensive C code, and just solve some new, more sophisticated problems together. So let's consider how we can go about solving problems involving data. Like case in point, phone books are a good example insofar as they represent a decent-sized data set that ideally is in fact sorted alphabetically or otherwise. And in the real world, like we are searching for, we are sorting information all of the time. Like odds are within the past hour or so, all of us have used Google or some search engine in some form. How does Google get us search results like that? Well, they've probably used some kind of very clever layout in their server's memory to get us answers really quickly. So we'll begin to think about, especially when data gets big, how we can use this kind of hardware, but and on top of which we'll write software to solve actual problems. So here again is like a little black chip on top of what's otherwise called a circuit board or a logic board inside of our Macs PCs and phones. If, though, we abstract this away and just assume that if this big chip here represents like 1 gigabyte of memory, 1 billion bytes, or 8 billion bits, well, surely we can just arbitrarily but consistently number them. Like this is byte 0, this is byte 1, byte 2, dot, 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 byte 1 billion, all the way down here in the bottom. So we can address our memory in this way. So let's forget about the actual hardware there, and now talk about what really is going on inside of the computer's memory, borrowing ideas from last week. So if this is just a canvas of memory, each of whose squares represents 1 byte of memory, how can we go about laying out information, be it names or numbers or web pages or anything else? Well, recall that we divvied this memory up into chunks last time, and we called this an array. And what was key about an array was that it was just a bunch of values back to back to back in memory, so-called contiguous. And it wasn't a huge deal last week that these things were contiguous in memory, back to back to back. But this week, it's actually going to really matter because it's because of that layout and because of last week's week 2 that we can actually solve problems efficiently in this week 3. So for instance, here are a whole bunch of numbers, and these numbers are stored in an array. And this array is of size 7, it would seem, because there's 1, 2, 3, 4, 5, 6, 7 numbers in this here array. And of course, you and I can see all of these numbers at a glance with sort of a bird's eye view. But the catch is that computers technically can only look at one location in memory at a time. Now, that's a bit of a white lie because computers are getting so darn sophisticated nowadays that different types, fancier computers, can maybe do multiple things at a time. But for our model today, we'll assume that a computer can indeed only look at one location at a time. So for instance, if you're searching for the number 50 among all of these values here, well, all of us in a split second can kind of spot it over there, third from the right. But a computer is going to have to look for it a little more methodically, more algorithmically, if you will, step by step in order to solve that problem. So a good mental model to have when it comes to what's going on inside of your computer is that these numbers are, yes, in an array, but they might as well be locked up behind closed doors, whereby in order to see each of those values and find one of them, the computer is metaphorically going to have to open up each of those doors one at a time, looking for the number that we actually care about. Now, it turns out we can treat this array of closed doors, gym lockers, if you will, much like an array. So this might be location 0, location 1, location 2, ... location 6. To be clear, there's 7 doors total, but as always, if you start counting from 0, it's n minus 1, which refers to the rightmost, or the last door, so 6 instead of 7. But there's indeed a total of 7 doors here. Just for parity with the lockers we were able to buy online, you might as well think of these as red doors, behind which are all of those numbers. So if the goal at hand now is to sort of mimic what's going on inside of a computer, I bet we could figure out how to find information among these doors. And this is just a problem to be solved. In the world of computing, this is the problem of searching, not surprisingly. And what does that really mean? Well, if we go back again to week 0, where this is computer science, like this is problem solving, what's the input to this problem? Well, we have an array of 7 doors that might as well be locked up behind these doors. And we want to get as output a Boolean value, like true or false. Yes, the number 50 is here, or no, it is not. So true or false, respectively, will get the job done. And inside of this, of course, is going to be, as always, some kind of algorithm, step-by-step instructions for actually solving this problem. So how, then, would a computer concretely go about searching for numbers behind this door? Well, maybe just for fun, we went ahead here and printed out some Monopoly money, some large versions thereof. And suppose we want to find very specifically the number, the dollar amount 50, behind one of these doors. Could we get maybe 1, maybe 2 volunteers? Behind these 7 doors are now dollar amounts, namely all of the available Monopoly dollar amounts. And if we want you to find the number 50, you can go about this in a bunch of ways. Like, you could go about just opening random doors, but that's not necessarily very repeatable. That's not very algorithmic, step by step. So let me propose that you do something super simple. Start at the left door and work your way to the right. And just so everyone knows what's going on, go ahead and show the world what number you've pulled out of each of these lockers. And the first locker is 20. That is correct, not 50.
500.
Yes, so incorrect.
10.
10, not correct.
Just O of n search time.
Not correct.
Trying to demonstrate the speed of linear
100,
search.
not correct.
1.
1, not correct, hopefully. Last door. And a round of applause, if we could, for finding the number. OK, so if you don't mind, before we transition to a better algorithm, because frankly that was pretty bad, but it wasn't incorrect in the sense that he was doing anything wrong. He sort of just had some bad luck. And frankly, if I hadn't sort of led him to that path from left to right, I could have proposed more cleverly that you maybe start from the right, and then boom, the problem would have been solved. But in general, if data isn't necessarily cleanly laid out by us humans in this very manipulative approach, like maybe it's going to be at the beginning of the array, maybe it's going to be at the end of the array, you really don't know. So you might as well have one methodical approach, step by step, and just do it again and again. So I think even though that felt increasingly awkward because you didn't find the 50 till the end, that was kind of as good as you could have done in general. And let me propose, before we try a second algorithm, if we take a look at some pseudocode here, I dare say what you implemented with my sort of encouragement was something called linear search, literally walking in a line from left to right. And if we kind of take the fun out of searching for money behind doors, we can make this more algorithmic with pseudocode, English-like code, but written in very terse language. You did, for each door from left to right, if 50 is behind the door, ideally, then you would have returned true. And that's when everyone applauded, of course. Else, if not, you might return false at the very end of this code. So we got lucky, 50 was there. But if you hadn't, you might have decreed, oh no, there's no 50, so I returned false. But notice the indentation here, just to highlight a key detail. I'm only returning false once I'm done with that loop. For instance, if I had poorly implemented this pseudocode like this, indenting that return false and only doing it conditionally if 50 is not behind the door. I know we're putting you on the spot here, but do you want to conjecture why this would be bad if you spot the mistake?
If you put false right after else, that means once we search the first door and we don't find 50, it'll just return false and the program will finish.
Exactly. So this code would indeed be a bad implementation, incorrect, because only if the 50 is behind the first door would it ever work correctly. We would otherwise bail out and return false prematurely. So this version here is indeed correct, but can we do better? Well, the numbers that were behind the doors for you, were they in any particular order?
No, they were randomized.
No, so we kind of set you up for failure in that sense. So if you don't mind, let's go ahead and pass the mic over. And secretly, behind me a moment ago, Yulia was kindly sorting all of those same dollar amounts behind the doors. And the question at hand now for you is going to be, find the number 50. But let's do this a bit like the phone book in week 0, where let's start in the middle. And if you recall from week 0, then let's go left or right accordingly. So what's behind the middle door? And we have?
It's 20.
20. So not correct, but what do we now know? 50 is in which direction?
To the right.
All right, so to the right. So go to the middle of the right. So that leaves you with these 3 lockers. In that middle door now?
It's 100.
100. So too big. So what do you now know?
It's going to be to the left.
Has to be, logically, if it's there at all, in between those two. And now we get your round of applause much
50.
faster than before. All right. So this then, if I can step over here before we give you a parting gift, this is where we left things off a moment ago. And in linear search, line from left to right, we checked each door. But just to make things a little geekier now and a bit more quantitative in nature, that really is the same thing as slapping numbers on this problem, whereby the first door we're going to call 0. The last door we're going to call n-1 if we start to treat these lockers not as physical objects, but as arrays instead. So in that same spirit, let me propose that when we found the number 50 this time, we took a fundamentally different approach, just like week 0 when we did divide and conquer, aka binary search. Binary implying we split the problem in 2, and 2, and 2 by going left or right each time. And the pseudocode that you might have arguably just implemented looks a little something like this. If 50 is behind the middle door, well, we got lucky, and we can simply return true right away. But if it's not, if 50 is less than the value at the middle door, we could have gone left, even though you didn't need to. Else, if 50 is greater than that of the middle door, we could search right, and you did do that. But there's a 4th scenario here. And we talked a bit about this in week 0. Do you spot what other scenario I might want to consider? If it's either in the middle or to the left or to the right, what else might happen? So what else might happen? It was that 4th scenario, yeah. So it might not be there at all, right? I could have really set you up for failure by not putting the 50 there. And in code, though, we need to handle that, because I conjectured in week 0, when you don't handle all possible scenarios, that's when the computer crashes or freezes or just something goes awry. So if there are no doors left, you sort of run out of possibilities. Logically, we had better make sure we return false. So before we give you both maybe one final round of applause, wonderfully, Monopoly makes its own Harvard edition for Cambridge, so we have a nice parting gift for both of you today. Thank you both for coming on up. All right. So just to now make that algorithm a bit more quantitative, instead of just saying middle, 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 let's use a bit of array syntax here now too. So this is the same exact pseudocode for that algorithm, binary search. And so the first condition is the same. If no doors left, just return false. But if 50 is behind doors bracket middle, and again, I'm sort of stealing some syntax from last week where we introduced square brackets for arrays, but I'm still using pseudocode. So this isn't C per se. But by doors, I mean the array known as doors. Bracket middle, I mean whatever the middle number is, the middle index is, go there. If you found it behind the doors bracket middle, return true. Else, as we enacted a moment ago, if 50 is less than the middle door, then go ahead and search what? Well, instead of saying search to the left and search to the right, let's make this again more precise today. Search the array of doors from location 0 all the way through location middle -1. So what do I mean by that? Here was the middle door, and even though this is not what we did a moment ago, if we were to go left, here's bracket 0, the first door. Here is middle -1, because if this is middle, -1 is immediately to the left. And this is why this algorithm would indeed have us searching the left half. Equivalently, if 50 is greater than doors bracket middle, then search doors middle +1 through doors n -1. Well, the end of an array, if 0 indexed, that is, you start counting at 0, this is always n -1. If this is middle +1 is here, and this is exactly what you just did, searching the right half of those doors. So we have this translation then from sort of the intuitive pseudocode from week 0 into now the more technical expression of arrays and array syntax here this week. And that's something now we'll begin to build on over the course of writing and implementing some of these problems here today. So if we now have algorithms that both solve the same problem, just like in week 0, which of those algorithms was better? The first one, which we called linear search, or the second one, which we called binary search? They're both correct, I would claim. So which is better? Which is better design? 2. And why do you say that?
Faster.
OK, so 2 is more efficient insofar as the second algorithm, if I'm thinking back, only took 3 steps. She only had to open up 3 of the doors, whereas the first algorithm, linear search, actually took as many as 7 steps. And in fact, we'll see some math underlying this. But it would be nice now if we could really compare the design of, the efficiency of algorithms a little more rigorously than just saying one is better than the other. Let's see if we can slap not some numbers on it, but maybe just some very simple arithmetic or algebraic formulas that allow us to compare 2 algorithms, so that in the real world and in problem sets and in projects in the future, you can sort of make a more quantitative claim as to which approach is indeed better. All right, so let's actually translate some of this to a little bit of code here. How could we go about implementing something like linear search? Well, let me do this. Let me go over to VS Code here. Let me propose to create a new program called search.c. So I'm going to do code search.c. And in here, I'm going to use the CS50 library at the top so I can get input. I'm going to use standardIO.h so I can print stuff out on the screen. I'm going to use int main void, because for today, I don't really care about command line arguments for this particular program. And let me start with an array of values. Suppose I want to implement in code the idea of these lockers containing those random values initially, and implement in C the very first algorithm we enacted with our volunteers, which was searching from left to right. Well, it turns out in C, I can create an array recall by saying I want integers. I want the array to be called numbers. And then inside of square brackets, I can specify how many elements I want. Maybe I want 3, like last week. But in this case, I think I want 7 this week to represent each of these lockers. But it turns out you can initialize an array without even using getInt or the like. You can just specify in empty square brackets that that whole array should equal the following inside of curly braces. So this is one new use of curly braces, but it's a handy trick when you want to create an array that has specific values like 20, 500, 10, 5, 100, 1, and 50, which just happens to be the exact order in which the dollar amounts previously were behind those lockers. So what does this line 6 do at the moment? It creates for me an array of size 7 and initializes it to that sequence of values from left to right. It is not strictly necessary to bother putting 7 there, and it's probably best not to, because the computer, specifically the compiler, will figure out how big the array should be based on what you typed inside of those curly braces. And you're just inviting a mistake if you put a number over here that's supposed to match the total over here. At some point, you're probably going to err. All right, so if that gives me then an array of size 7, let me go ahead and ask the user, what number do you want to search for, much like I verbalized before. So int n equals get int, and I'll prompt the human for a number, as with this kind of prompt. How do I now implement linear search? Well, based on the constructs we explored in week 0 and week 1, we had conditionals and loops and variables and Boolean expressions and the like. What is probably like the feature of a programming language that we're going to need to search from left to right to implement linear search?
Loops.
A for loop, probably, or a while loop, but a loop in general. Why? Because I could use like 7 conditionals, and I could say if the numbers bracket 0 equals this value, then return true. Else, if numbers bracket 1 equals this number, then return true. But that's not very general purpose. If we're going to have all of these conditionals, let's just have one that asks the same question by just changing some variable. And a for loop is often the paradigm. So for int I equals 0, I is less than 7, I plus plus, and this code alone sort of sets me up to implement what our first volunteer did from left to right with the lockers. What's the question I want to ask? Well, does the array of numbers at the current location I equal the number n that we're actually looking for? So does the number behind the first door, second door, third door actually equal 50, for instance, or whatever's typed in? And if so, let's go ahead and print out something clear like found \n. Else, I don't think I want to do this. Printf not found. So let me for a moment sort of poorly implement this. What have I done wrong with this code? Yeah, in the back. Yeah, I don't want the if in, I want the if inside the for loop, but not the else inside the for loop. Why? Because that would be the equivalent of starting at I equals 0, opening the door, and then concluding I have found or not found the number without even allowing us a chance to keep going, because we're going to spit out sort of unilaterally not found, even though we just haven't found it yet. So I don't think I want to do that, but I think what I can do, for instance, is as per the slide a bit ago, if I, at the end of my loop, get all this way, then I think I can print not found. But I think logically, even this might be imperfect. So let me go ahead here and do make search, enter. Seems to have compiled OK. So new syntax errors, /search, enter. What number do I want to search for? I'm going to go ahead and type 50 and hit enter. And still I have a logical bug. It's saying found, but also not found. Why? Even though I moved that line of code outside the loop, which is correct, but there's still something wrong here. Yeah?
You gotta quit.
Yeah, the iteration still ends up leading us to this final line. Why? Because we're going to go all the way from 0 to the end of the array again and again and again, hopefully printing out found when we find it. But there's nothing stopping us from then executing line 16 before the program actually ends. But recall last week, we had a solution to this. Even main can return a value. And even though in week 1, it was sort of secretly returning the number 0, unbeknownst to us, it turns out, we now had the ability, as of week 2, to explicitly return a value anywhere in main that we want. And the convention, a little paradoxically, is to return 0 upon success, because that means all is well, and then return anything other than 0, like a positive integer, if anything has gone wrong. And we use positive integers because it could be this thing that goes wrong, this thing, this other thing. Lots more can go wrong than can go right when writing code. So I think what I could do here is after printing found, I could return 0 to signal success, even though the human's not going to see anything different. And down here, I could actually return 1 to signify failure. And recall with the little command trick, I could do $, question mark, and actually see what that value is. But for our purposes, what we really care about is that main returns when we are done solving this problem, either inside of the loop or ultimately outside. So let me try this again. Make search, /search. Let's search for, again, the number 50, enter. And indeed, it is found. and only found. Let's do this again. /search. Let's search for the number 2, which is not in that array. And I should see and only see not found in this case. So this then would be the code for linear search. Any questions on what we just did here? Yeah? A really good question. What if we don't initialize the array? Well, honestly, in programming, a very good answer to that question is just try it out and see what happens. So let me create an array of size 7 with no values inside of it. Let me reopen my terminal window, do make search, and the compiler doesn't seem to mind that. If I go ahead and now do /search, enter, I'll be prompted for a number. I'm going to presume to search for 50, even though I don't know what's in there. Enter. And at least it was not found here. Let me go ahead and try again. Let me search for the number 2, not actually found. Search for the number 1, not actually found. And I could poke around all day long, but it turns out I'm probably just getting lucky here. Why? Well, this loop, no matter what, is going to check 7 locations. But I have not put anything in any of those 7 locations. But recall from last week, we sometimes saw those garbage values, sort of remnants of memory that, of course, exist, but maybe had been used for some other value previously. At the moment, I think I'm just getting lucky that among the first 7 locations in the computer's memory, I just didn't end up with a garbage value 50 or 2 or 1. But if we played this game for a while, I bet I could come up with a number that actually works. And let's see, at the risk of a demo not going according to plan, let me do /search. Let's search for 0. Still not there. Let's search for 3, 4. OK, we're going to have to do this all day long to actually find the values. There's 4 billion possibilities. But at some point, we would get lucky, and it would say found, but only by chance. So in short, do not do that, since it is wrong. All right, so let's transition then to maybe a better version of this. What if the numbers are actually sorted? And frankly, what if they're not actually numbers at all? Let me go back into this code. Let me throw away the contents of main. And let's do something maybe now with strings instead, just so it's more like searching an actual phone book. So I'm going to create an array of strings called strings, for lack of a better name. And much like a certain game with which you might now be familiar, we might have a string for battleship and boot and cannon and iron and thimble and top hat, though this does vary by country based on which version of Monopoly you actually have. Then let's go ahead and prompt the user for a string s using getString and ask them for a string to search for. And then let's do a for loop again. For int I equals 0, I less than 1, 2, 3, 4, 5, 6 values. I'm hard coding 6, and I don't like that, but we'll come back to that idea in general of figuring out what the length of that array might be. But for now, I'm just going to hard code it. But that's not indeed good practice. I++. Inside of the for loop, now let me go ahead and do this. If the ith string, or the strings at location I, equals s, then let me go ahead and print out as before, found. Let me not make the same mistake as before. So let me immediately return 0 to signal success. But if we don't find it anywhere in that array, let's go ahead and print out not found. And then let's go ahead and return 1 just as before. So the only thing that's different now is I'm using strings instead of integers. But I'm otherwise looking for the ith string that might very well have the same value as s, what I have typed in. All right, let me go ahead and open my terminal again. Run make search again. So far, so good. /search. Let's search for maybe the thimble. Enter. It's not found. All right, maybe it's too far away. Let's search for again. Battleship. Enter. Not found. How about the top hat? Enter. Not found. And I could do this 3 more times, but I'll claim that it's never going to find any of these strings. Does anyone have a suspicion as to why or how we might solve? Why is this not working? Yeah. Yeah, well said. So it turns out, and this is super subtle, equals is not how you can compare strings. And we'll see why, in fact, in greater detail next week. But for now, equals works fine for integers, for longs, for chars, and a bunch of other data types as well. But it doesn't actually work for strings. And for today's purposes, it's really because strings can be different lengths. And equals is only going to compare 2 values. But a string might be 3 characters, 4 characters, 5 characters, depending on how many characters I have typed in. equals equals is not powerful enough or wise enough to actually solve that problem. However, this is such a common thing to do, like in our phones and on Google and the like, to compare strings that humans have typed in, that there is, in fact, a solution for this. And so, in fact, we'll introduce today another function from the string.h header file that we introduced last time. Recall that inside of string.h was the declaration for strlen, S-T-R-L-E-N, which would figure out the length of a string based on the null character and everything we talked about last week. But within the same library, as per CS50's documentation, there's another function called strCmpare, or strcmp for short. And if you were to pull up the documentation for that particular function, you will see that its prototype actually takes two strings as input, called S1 and S2, though we could call those any two things. But what's noteworthy about this function is that its return value is sort of ternary. It can return one of three different things to us. The function can return an int less than 0 if S1 comes before S2. It will return 0 if S1 is the same as S2. And it will return an int greater than 0 if S1 comes after S2. So strCmpare is more powerful than just saying yes or no, these strings are equal. It can actually be used to alphabetize strings as well. Because what it's essentially saying is alphabetically S1 comes before S2, or S1 and S2 are the same, or S1 comes after S2 alphabetically. And alphabetically is a bit of a white lie. It's technically ASCII-betically, because what's being used is the ASCII values. So lowercase characters are going to be treated different from uppercase characters. So we say ASCII-betically because it's literally comparing the ASCII codes. But for now, I'm going to avoid that problem by just using lowercase everywhere. But if I want to use this function, let me go back over to my code here. And instead of doing equals equals, I have to use a function here called strCmpare, passing in one string like strings bracket I, and then the second argument, aka S2, is going to be the string I want to compare against. But I want to check the return value of that function. And again, what value should I check for if I want these things to be equal? So 0 was the operative return value. So what I want to do is this. So this looks at a glance like way more complicated than it really needs to be. But all it's doing is calling a function called strCmpare, passing in two strings as input, generally known as S1 and S2, comparing them. And if they are exactly the same character for character, left to right, strCmpare, per its documentation, will return 0. I don't care about less than 0 or greater than 0 because I'm not trying to sort anything. I'm just trying to return true or false, yes or no, we have found this string. So to use that function, just like strlen, I need to include string.h at the top. Let me open my terminal window. Let me rerun make search. So far, so good. /search. Now let me search for thimble in the exact same array, crossing my fingers, and voila, now we have found thimble. And just for kicks, I'll do it twice more. Battleship, which failed previously, but this time not. Top hat failed previously, but not. This time I'll search for something like a car, which is not in the array. Enter, and that is in fact not found. So a subtlety, because strings, as we'll soon see all the more, are indeed a bit different from just comparing simple values like integers, chars, and the like. Questions on what we just did with strCmpare or searching for this thing linearly in this way? All right, well, why don't we graduate to like more of an actual phone book? Right now, I'm just kind of searching for arbitrary strings. Let's make something that's a little more involved, but uses these exact same ideas. Let me go ahead and code up a file called phonebook.c. At the top of the file, I'm going to include those exact same files. So include cs50.h, include standardio.h, include proactively this time string.h. I'm going to create my main function. No need for command line arguments today. Inside of main, I'm going to give myself now two arrays just so we actually have both names and numbers. So for instance, I'm going to do this. An array of string called names. And in that array, I'm going to have three of us. So inside of curly braces, I'll have Yulia, who kindly volunteered earlier as well, me, and how about John Harvard as always, whose number we'll search for. Then let me go ahead and keep track of not just the names in this phone book, but also the numbers. So string numbers, and then equals. And then the numbers I'm going to put here are going to be, for instance, how about +1, -617, 495, 1000. Yulia and I will have the same Harvard directory number, so +1, 617, 495, 1000. And then John Harvard will have his old number, +1, 949, 468-2750, which, just for an Easter egg, you're welcome to text or call sometime. All right, so now I have two parallel arrays, if you will, from left to right that are both mapping names in one array to numbers in the second array. And actually, if I want to keep this thing sorted, that's kind of on me, and I don't really care about that for now. But if I wanted to sort this, notice that I'm actually going to need to move Yulia's name there and move Yulia's number to the end here, but otherwise we still have an array of size 3 for each of names and numbers. Let's go ahead now and search for someone's name and therefore find their number. So let's prompt the user for a string called name using getString and ask them, what name do you want to search for in this phone book? Just like before, let's use linear search to keep it simple. For int I equals 0, I less than 3 this time because there's 3 people involved, I++. Then inside of this for loop, let's do the same correct technique as before. If the return value of stir compare passing in 2 values. What are the 2 values I want to pass into stir compare here in order to check if we have found a person's name? What could the first one be? Feel free to shout it out.
String index I.
What am I searching for? The user has typed in name, but I want to compare it against. Yeah, I think names bracket I. So like if the ith name is the same thing as the name the human typed in, and I know that because stir compare will return 0 for me, then I can go ahead and say, just as before, found. And just for kicks now, let's go ahead and actually print out what that person's number is, rather than just say found, quote unquote, by outputting numbers bracket I. So this is to say, if we find in names bracket I the person's name that we're searching for, then go ahead and print out that same person I's number. And so that we don't accidentally say not found later, let's return 0 immediately. Otherwise, down here, let's say not found with no number, of course, and then return 1 to signify error. So if I hide my terminal window, this is sort of a simple implementation of a phone book on like an iPhone or on an Android phone when you're searching for your contacts, top to bottom or left to right. So let me go ahead and run this in my terminal. I'll do make phone book, enter. So far, so good, /phonebook. And if I search for John by his name, properly capitalized, enter, I indeed found John Harvard's number to be +1 949 468 2750. This then is correct. What, though, is arguably poorly designed about this program, even if you yourself are still newish to programming? What's bad about this design here, might you say?
Dictionary. You can use a dictionary instead to house those key values.
What's bad?
Uses too much data.
Yeah.
Unnecessarily.
Good. So I don't like that. The fact that I'm using this so-called magic number, which means just hard coding a value that you're trusting is not going to change, or that you'll remember to change it. I don't like this. So that's a really good observation. What else might you not like instinctively, even if, again, these concepts are new? And often, yeah. Yeah, we're again on sort of the honor system here that we have these 2 arrays, and the onus is on me, the programmer, to make sure that they line up. And case in point, when I manually went back a moment ago and moved Yulia to the end of the names array, I had to remember to move her number to the end of the numbers array, and that just strikes me as very fragile, so to speak, right? It's just too easy for me or a colleague to screw up this code by forgetting that sort of lower level detail. We're just trusting that names and numbers do stay aligned, and they have the exact same number of people in them, and the exact same number of numbers in them as well. So we have an opportunity now to sort of do better than this. And besides arrays, which we've already seen do solve a lot of problems by letting us use one variable to store bunches of things, wouldn't it be nice if there was another type of variable that's not int, that's not string, that's not char, that's not float, or any of those that we've seen already? Wouldn't it be nice if there's like a person data type in C, where I can actually create a person in my code, and a person in this world shall have a name and a number? Heck, if we were implementing students, maybe a student could have a name, a number, an email address, a Harvard ID number, or Yale ID number, or the like. You could imagine encapsulating, so to speak, a bunch of different types of data inside of one larger data type. And generally, when we talk about data structures, we mean exactly that, some kind of container for multiple types of data. So a custom data type, if you will. So for instance, if I wanted to create an array of people, wouldn't it be nice if there's a data type called person? So I could use code like this. Give me an array of people, and I don't know how many yet, but give me an array of people, each of which is of type person. So instead of string, instead of int, I'm saying person. And in English, I'm pluralizing the name of the array as obviously people instead. But that doesn't exist with C. Like there are no student data types. There are no people data types. There are no professor data types. Any of these things that you might imagine in the real world don't come with C. All you get are strings and ints and floats and those lower level features. But if we know a person, for our purposes, we'll have a name and a number. Well, why don't we just give them a name and a number, but somehow encapsulate this name and number in a bit of new syntax? And so the new syntax we will introduce today is that of creating your own type that is a structure specifically. And we'll see more of these over the course of the term. And even though this looks a bit cryptic, what this chunk of code here is saying is define a type that is itself a structure, inside of which is both a name and a number, which are both strings in this case, and call that whole new structure person. So as soon as the compiler gets to the semicolon, a person data type does now exist. And inside of that data type is two things, a name and a number. Now, as an aside, I deliberately use string here for both name and number. I used string in my code a moment ago for those phone numbers. Why did I use a string instead of an int or even a long for my phone numbers? That wasn't actually a mistake. Yeah. Yeah, like the hyphen, the country code, maybe parentheses if you format your number differently. And so a good rule of thumb actually is that even though you and I in the real world might call certain thing numbers, like social security number in the United States, or phone number, or ID number, if there might potentially be other punctuation or symbols in that number, and frankly, more generally, if it would make no intuitive sense to perform math on something you call a number, and I can't think of a scenario where you'd want to perform math on a phone number, you probably should store it instead as a string instead, and use actual integers, actual longs for things that mathematically or computationally make sense to be treated as literal numbers instead. So if I now have this new feature whereby I can define a custom data type in my phone, for my phone book, I think I can implement a brand new version of this program that's going to be a bit more verbose, but it's going to allow me to solve this problem better. So let me go back to VS Code here, and you'll see in this code where we left off. I'm going to go ahead and delete all of this just for now, and I'm going to whip up a slightly better version, I will claim. Outside of my main function, I'm going to do exactly what we just saw on the slide. I'm going to define a structure inside of which is a name of type string and a number of type string, and I'm going to call that whole thing a person. Turns out style 50, and particularly the program we're using underneath the hood, prefers, weirdly, that you put person on the same line as the curly brace. So just FYI, if you run style 50 and you see that it moves as such. Inside of main, I'm going to now give myself an array of type person called people of size 3. So still, I'm not going to solve all of today's problems. I still don't like the fact that I'm hard coding a 3, but I just want to demonstrate for today's purposes how we can use this here feature. So I now have an array of 3 people, and each of those people is by definition a person, and a person, we now know, contains a name and a number. So how do I initialize this array? It's not as simple as just using like getString once. I clearly need to use it twice, but I won't even do that. I'll just hard code the values for demonstration's sake now. Let us update the first person in the people array. So this is week 2 syntax, and set the name of that first person equal to quote unquote David, semicolon. Then in that same person structure, go into their number field and set that equal to +1 617 495 1000 semicolon. So what here is new? Well, of course, people bracket 0 isn't really new. Like we did that last week. If the array is called people and you want the first element, you use bracket 0. But what is new today is this dot operator. Once you've created a structure inside of the computer's memory, if you want to go inside it and access the things that compose it, like name and number, you just use a dot like this. And that means go inside the first person and access their name, set it equal to quote unquote David, and do the same thing now for their number. So even though, yes, this stuff is new here, the only new operator, so to speak, today is really that same dot. All right, let's go ahead and initialize the other two people, just so we have an array completely defined. People bracket 1 dot name will be John as before. People bracket 1 dot number will be John's number, which was a little different, +1 949 468 2750. And then lastly, people bracket 2 dot name equals quote unquote Yulia. And then people bracket 2 dot number equals the same as mine, +1 617 495 1000. So now, even though this is more of a mouthful, and let your mind wander to the reality that like we could just use a loop to do this a little more cleanly and use getString and make it interactive, but I really just want to demonstrate the typedef and the struct and this new dot operator. Let's now search for someone's number. So let's ask the user for a string called name using getString as before, prompting for that name. Then inside of a for loop, for int I equals 0, I less than 3. Again, don't love that, but we're focusing on one problem at a time, not this other one. I++. Inside of the for loop now, same as before. If the return value of stir compare, passing in the current person's name and the name that the human just typed in returns a value of 0, then inside of that, let's go ahead and print out found %s \n and plug in people bracket I, but I want to see their number, so I do dot number instead. Now I can return 0 for success. Down here I can print out not found to indicate failure, and down here I will return 1. So the only new stuff in this program really is the fact that I have now invented a new data type called person that we can now use in our code, and I'm accessing the individual fields or attributes of that new structure by using this new dot operator, which goes inside of that custom structure. All right, if I didn't screw up, let me go ahead and make this phone book. So far, so good. /phone book, enter. And now if I type in John, enter, I have, in fact, found John's number. And if I go ahead and search for someone else, for instance, like Brian, who's not in the phone book, he, in fact, is not found.